Close your eyes for just a moment. Now imagine opening them again, not here, not on Earth, but standing on a surface no human being has ever touched. The sky above you is not blue. It is a deep, burnt orange, thick and heavy, like the inside of an old amber stone. There is no wind sound, because the air here is so dense that sound itself behaves differently. If you spoke right now, your voice would feel strange to you, deeper, closer, almost as if the atmosphere itself were listening. You look down. Beneath your boots is not sand, not rock in the way you know it. It is something colder, something stranger, grains of frozen organic material, fine as powder, resting atop a crust of solid water ice as hard as granite. The ground feels firm, but everything around you whispers that this is not your world. In the distance, something catches your eye. A dark, glassy surface stretches toward the horizon, perfectly still, mirroring the orange sky above it. For a moment, you might think it's a lake. And in a sense, it is. But it is not water. It is liquid methane, a lake of liquid natural gas, sitting calmly under a sky that never lets the sun shine through directly. Above you, the haze is so thick that you cannot see stars. You cannot even see the sun as a clear disk, only a dim, diffused glow, swallowed by an atmosphere 10 times thicker than Earth's. Listen, for a moment, to the silence around you. Not true silence, because true silence does not exist here, not in the way you might imagine. The atmosphere is too thick for true silence, but it is a different kind of quiet than anything you have ever experienced. No birds, no insects, no distant traffic, no rustling leaves, none of the 1,000 tiny background sounds your mind has learned to simply ignore over a lifetime on Earth. Just the faint, deep hush of dense air settling around you, and somewhere, far in the distance, the soft, almost imperceptible suggestion of liquid gently moving against a shoreline you cannot quite see through the haze. This is Titan, the largest moon of Saturn. A world so strange, so alien, and yet so eerily familiar, that scientists have spent decades trying to understand exactly what it would feel like to stand where you are standing right now. But here is the question that will guide everything you are about to discover. If Titan has lakes, and rain, and rivers, and seasons, and even something that resembles weather, then why does NASA keep calling it one of the most mysterious places in the entire solar system? What is it about this moon, smaller than Earth, colder than anything you've ever experienced, drenched in chemicals that should not allow for anything resembling life, that keeps pulling scientists back, mission after mission, decade after decade? Because the truth is, Titan does not just look alien. It behaves like a world that shouldn't exist. It has rivers carving valleys, exactly like Earth. It has rainfall, evaporation, and clouds, exactly like Earth. It has dunes that stretch for hundreds of kilometers, shaped by wind, exactly like Earth. And yet, almost nothing on Titan is made of the materials we associate with those processes here at home. The rain is not water. The rivers are not water. The sand in the dunes is not sand. Everything you recognize is built from something else entirely. So when you stand on Titan, when you really try to imagine standing on Titan, you are not just visiting another moon. You are stepping into a mirror of Earth, built from entirely different rules. And the deeper scientists look into this moon, the more they begin to suspect that underneath that thick orange haze, in oceans hidden far below the icy crust, something extraordinary might be happening. Something that could change how we think about life itself. But to understand what that something might be, we first need to understand what it would truly feel like to be there. To stand on that frozen ground. To breathe, if you could breathe, that strange hazy air. To watch methane rain fall in slow motion through skies 6 times less gravity than Earth's. So let's begin this journey the only way it deserves to begin. Quietly, patiently, one slow step at a time, into the haze. Because what you are about to witness is not just a description of a distant moon. It's an invitation to experience an entire world, one drop of frozen methane at a time. Over the next 2 hours, you are going to experience Titan in a way almost no documentary allows, not as a list of facts, not as a chemistry lesson, but as a journey, slow, immersive, and continuous, through every layer of what it would actually feel like to stand on this moon, breathe its strange, thick air, and look up into a sky unlike anything Earth has ever offered. You will discover why Titan's gravity would let you leap further than any Olympic athlete ever has, and why that single fact changes everything about how a human body would move across its surface. You will discover why the temperature there, nearly 290 degrees below zero, does not behave the way cold behaves on Earth, and why your body would face dangers that have nothing to do with simply feeling cold. You will discover why the sky above Titan is orange instead of blue, and why that orange haze hides one of the most important discoveries in the history of planetary science. You will discover the truth behind Titan's rivers, lakes, and rain, and why NASA scientists have spent over 20 years trying to understand a liquid cycle that mirrors Earth's water cycle almost perfectly, except built from chemicals that, on our planet, we associate with fuel, not weather. You will discover what it would sound like to stand near a Titan shoreline, and why the unique density of its atmosphere means that sound itself would behave in ways no human has ever personally experienced. You will discover the strange, almost impossible dunes that stretch across Titan's equator, dunes made not of rock, but of frozen organic material, shaped by winds scientists still don't fully understand. You will discover what lies beneath Titan's icy crust, a hidden global ocean of liquid water, sealed away from the surface, and why some researchers believe this hidden ocean might be one of the most promising places in the entire solar system to search for life. You will discover why Titan's chemistry produces complex organic molecules similar, in some ways, to the chemical foundations that may have existed on early Earth, and why this single fact transformed Titan from a curious moon into one of the top targets in the search for life beyond our planet. You will discover the extraordinary mission currently making its way toward Titan right now, a flying robotic explorer designed to drift across its skies and land in multiple locations, becoming humanity's first true visit to its surface. And finally, you will discover why so many scientists describe Titan not simply as a moon, but as a preserved, frozen version of a process that may have once happened, slowly, patiently, somewhere else, long before our own world ever existed. This is not simply a tour through a strange place. It is a tour through one of the most carefully studied, deeply debated, and quietly thrilling mysteries our solar system has ever offered us. Because Titan does not just resemble Earth, It rewrites what we think a world needs in order to behave like one. And perhaps, by the end of this journey, you will understand why so many scientists who have spent their entire careers studying other planets, Mars, Venus, the icy moons of Jupiter, eventually find themselves quietly drawn back, again and again, to this one particular moon. Not because Titan is the most dramatic place in our solar system, not because it offers the most violent volcanoes, or the most extreme storms, or the most spectacular visual scenery, but because Titan offers something rarer than drama: patience. A world that has spent over 4 billion years quietly working through the same fundamental questions we ourselves are still asking. What does it take for chemistry to become biology? How rare or how common is the line a world must cross to go from interesting to alive? Titan may not have crossed that line, or it may have crossed it quietly, in some small hidden corner of its dark internal ocean, in a way we have not yet found the means to detect. Either way, the only way to know is to keep watching. Patiently, carefully, the same way Titan itself seems to do everything. So take a slow breath, and let's step, together, into the orange haze. Before we take that first step, it's worth pausing on something remarkable. Humanity has known Titan existed for far longer than most people realize. In March of 1655, a Dutch astronomer named Cassini-Huygens pointed a simple hand-made telescope towards Saturn and noticed something orbiting it, a faint point of light, moving steadily night after night, tracing a slow path around the ringed planet. He had discovered Titan, becoming the first human being in recorded history to know this moon existed at all. At the time, Huygens had no way of knowing what he had actually found. He couldn't have imagined orange skies, or seas of liquid methane, or a hidden ocean of water sealed beneath kilometers of ice. To him, Titan was simply a point of light, a small, faint companion, quietly circling a planet already considered one of the most beautiful objects in the night sky. It would take over 350 years and a spacecraft bearing his own name before humanity finally understood what that faint point of light truly was. That journey alone is worth sitting with for a moment. The Cassini-Huygens mission, named in honor of both Cassini-Huygens and the Italian astronomer Giovanni Cassini, launched from Earth in October 1997. It traveled for nearly 7 years, looping past Venus, past Earth again, past Jupiter, gathering gravitational momentum from each encounter, before finally arriving at Saturn in 2004, a journey covering more than 3.5 billion kilometers, longer than the distance to Saturn itself, because of the wide looping path required to get there, using the fuel available at the time. When Cassini finally entered orbit around Saturn, it carried with it the small Huygens probe we explored briefly, already named, fittingly, after the very astronomer who first noticed that faint point of light over 3 centuries earlier, finally completing the journey he could only imagine. So when you imagine standing on Titan's surface, you are standing somewhere humanity first glimpsed, as nothing more than a flicker of light, centuries before any of the technology required to actually understand it had even been invented. Now, let's return to that first step. What would it actually feel like the moment your boot touched Titan's surface for the very first time? Most people imagine it would feel heavy, Cold, crushing even, like stepping into a frozen wasteland under the weight of an alien sky. But the truth is almost the opposite. The very first thing your body would notice is not the cold, it's the lightness. Titan's gravity is only about 1/7 of Earth's. To put that into a feeling you can actually picture, if you weigh around 70 kilograms on Earth, on Titan you would weigh barely 10. Your body would suddenly feel as though it had been carved from something lighter than itself. Every motion, lifting your arm, turning your head, shifting your weight from one foot to the other, would feel slow, floating, almost dreamlike. And if you tried to walk normally, the way you walk on Earth, you would likely stumble. Not because the ground is unstable, but because your own muscles trained for a lifetime of Earth's gravity would suddenly be far too strong for the world they were standing on. A single ordinary step, the kind you take 1,000 times a day without thinking, would launch you upward into the haze far higher than you intended. Scientists who study planetary locomotion have calculated something remarkable. A human being on Titan could jump nearly the height of a 2-story building using nothing but the strength of an ordinary leg. Not a sprinter's leg, not an athlete's leg. An ordinary leg, untrained, simply walking the way it always has except now, surrounded by 7 times less resistance pulling it back down. But that wasn't the strangest part, because Titan does not just have low gravity. It has thick atmosphere, shockingly thick. In fact, almost 1.5 times denser than Earth's air, sitting heavy and close to the ground. And when you combine extremely low gravity with extremely thick atmosphere, something strange happens to the way a human body would actually move through it. It would feel less like walking on the moon and more like moving underwater. Each step would feel slow and resisted, almost like wading through a gentle current, yet at the same time impossibly light, almost weightless. Researchers who have modeled this exact combination describe it as one of the strangest forms of human movement we could ever physically experience anywhere in the solar system, not floating, not falling, but suspended in something in between. Imagine, for a moment, what this would actually look like if you tried to run. Each stride would carry you forward in a long, slow arc, your body rising gently before drifting back down, the thick air around you pressing softly against your skin the entire time, like moving through a fog made of pressure rather than mist. Even a simple act, like jumping over a small rock, would turn into something closer to a slow-motion leap, your body rising calmly into the dim orange sky before gently returning to the icy ground far longer than your instincts would expect. And here is where the next mystery begins. Because if your body would move so differently here, what would it actually feel like for that body to be exposed, even briefly, to Titan's true environment? The temperature on Titan's surface hovers around -179 degrees Celsius. That is a cold so extreme that it does not behave the way cold behaves on Earth. It is closer to the temperature inside a deep cryogenic freezer than anything resembling a harsh Earth winter. At that temperature, exposed skin would not simply feel painfully cold. Within seconds, biological tissue would begin to freeze at a cellular level. Without a heavily insulated suit, one capable of managing both the extreme cold and the unusual atmospheric pressure, survival on Titan's surface would be measured in moments, not minutes. But here is what makes this even more fascinating. Despite that brutal cold, the thick orange atmosphere around you would not feel like the thin, harsh air of high-altitude mountain peaks. It would feel dense, almost heavy against your suit, the pressure pressing inward like an invisible weight resting calmly across your shoulders. And the sound. Sound on Titan behaves in a way almost no human has ever personally experienced, because of just how thick that nitrogen-rich atmosphere truly is. Scientists who study acoustic behavior in dense, low-gravity environments believe sound on Titan would travel further and resonate longer than on Earth. A distant sound, a methane wave breaking gently against a shoreline, or wind moving slowly across frozen dunes, might reach your ears with a strange, deep richness, almost as though the entire landscape itself were quietly humming. Yet, despite all of this strangeness, despite the floating steps and the freezing temperatures and the impossibly thick, sound-carrying air, there is something deeply unsettling that researchers have long puzzled over. Because if Titan's gravity is so weak, if its atmosphere is so heavy and dense, then how did it manage to hold on to that atmosphere at all for billions of years, when smaller worlds like our own moon lost their atmospheres almost entirely? This single question, how a small, icy moon orbiting far from the sun managed to keep one of the thickest atmospheres of any moon in the solar system, sits at the very center of one of Titan's deepest unsolved mysteries. And the answer, as you're about to discover, leads somewhere far stranger than anyone expected. But before we follow that thread, there's something else worth pausing on, because everything we just described about floating footsteps and impossibly thick air isn't theoretical. It's something humanity has already, in a very real and very limited sense, touched in January 2005. A small probe called Huygens, carried across the solar system aboard the Cassini spacecraft, separated and began its long descent through Titan's atmosphere. For over 2 hours, it fell gently through that thick orange haze, parachutes slowing its fall, instruments recording everything they could about the air pressure, temperature, and chemical composition surrounding it. It was, and remains to this day, the most distant landing ever achieved by a human-made object anywhere in the solar system. When Huygens finally touched down, it didn't shatter, the way many engineers feared it might if it struck solid ice. Instead, telemetry suggested it landed on a surface with the approximate consistency of wet sand or soft clay, firm enough to support its weight, yet soft enough to leave a gentle impression, exactly the texture you might expect from ground recently dampened by methane rain. For 90 minutes, before its batteries finally failed in the extreme cold, Huygens transmitted data back to Cassini, which relayed it across nearly 1.5 billion kilometers to scientists waiting anxiously on Earth. It sent back the first, and to this day, only photographs ever taken from the actual surface of Titan. Hazy, amber-toned images revealing small, rounded ice pebbles scattered across a flat, eroded plain, remarkably similar in shape and arrangement to stones found in a dry riverbed here on Earth, evidence, frozen in time, of liquid that had once flowed across that exact location. But that wasn't the strangest part of what Huygens discovered, because its instruments also detected something briefly, faintly, in the moments just after landing, a small spike in methane concentration near the surface, suggesting the probe's own heat, however slight, had caused a tiny amount of liquid methane trapped in the soil to evaporate around it. In other words, humanity's first and only direct surface measurement on Titan accidentally proved, within minutes of landing, that liquid methane existed in the ground itself, not just in distant lakes and seas, but soaked into the very dirt beneath where it came to rest. That single probe, operating for less than 2 hours on the surface of a moon nearly 1.5 billion kilometers from Earth, fundamentally confirmed what scientists had only theorized until that moment, and it left behind a question that has quietly lingered for over 2 decades since. If a single, stationary probe unable to move, unable to explore beyond the small patch of ground it landed on, revealed this much in 90 minutes, what might an actual mobile explorer, capable of flying across entirely different regions of Titan's surface, eventually discover? Why does Titan still have an atmosphere at all? It's a question that sounds simple, but it quietly unravels one of the strangest puzzles in the outer solar system. Consider Earth's moon. It is roughly the same size as Titan. It formed in the same general era of the solar system. And yet, our moon has almost no atmosphere whatsoever, just the faintest trace of gases, far too thin to matter. Mercury, despite being a full planet, also lost almost all of its original atmosphere long ago. Titan should have followed the same fate. It is small. Its gravity is weak. It sits far from the sun, in the cold outer reaches of the solar system, orbiting a gas giant that itself is bathed in punishing radiation. By every basic expectation of planetary science, Titan's atmosphere should have leaked away into space within a few 100 million years, drifting outward into the void, the way so many other small worlds eventually lost theirs. Instead, Titan holds onto an atmosphere so thick that it presses down on the surface with 1.5 times the pressure we experience here on Earth. Scientists soon discovered something remarkable when they began studying this question closely. The secret might not be Titan's gravity at all. It might be its temperature. Because Titan sits so far from the sun, surface temperatures remain locked in an extreme, stable cold enough to slow down the movement of atmospheric molecules dramatically. And when molecules move slower, they are far less likely to reach the speed required to escape into space. In other words, Titan's atmosphere isn't thick because Titan is strong. It's thick because Titan is cold enough to be patient. But that explanation, while elegant, only opened a deeper puzzle, because researchers studying the chemical composition of Titan's atmosphere noticed something they didn't expect. Nearly 98% of Titan's atmosphere is nitrogen, the very same gas that makes up nearly 80% of Earth's atmosphere. For a tiny, frozen moon billions of kilometers from the sun to share its dominant atmospheric gas with our own living planet felt, to many scientists, like an extraordinary coincidence. Except it might not be a coincidence at all. Because the deeper question is not simply why nitrogen, it's where did all of this nitrogen actually come from? For decades, the leading theory suggested that Titan's nitrogen came from ammonia ice, locked inside the moon since its formation, slowly converted into nitrogen gas by sunlight and chemical reactions over billions of years. But when the Cassini spacecraft, NASA's long-term Saturn orbiter, finally measured the precise chemical signature of Titan's nitrogen in extraordinary detail, the numbers didn't match what that ammonia-based theory predicted. The nitrogen looked different. its isotopic ratio essentially a chemical fingerprint that reveals where a substance originally came from more closely resembled nitrogen found in ancient material from the very outer edges of our solar system, similar to the icy bodies found in comets from the distant Kuiper belt. This discovery quietly suggested something extraordinary, that Titan's atmosphere might not have formed gradually from materials trapped within the moon itself. It may have arrived already in its early form, locked within primordial ice that built Titan from the very beginning, material that originated from the cold, distant edges of the solar system, far beyond where Saturn even orbits today. If true, this would mean Titan is not simply a strange moon orbiting a beautiful ringed planet. It may be a surviving fragment of the earliest chemistry of our solar system chemistry that, on most other worlds, was destroyed, altered, or lost entirely as those worlds evolved. Titan, by contrast, may have frozen that early chemistry in place, like the universe placing a single sample under glass and saying, quietly, "Preserve this." Yet another mystery emerged when scientists tried to pin down exactly when and how that primordial nitrogen first arrived. One leading hypothesis suggests Titan formed gradually within a cold, slowly cooling disk of gas and dust that once surrounded the young Saturn, shortly after the planet itself finished forming. Within that disk, icy particles rich in nitrogen compounds would have slowly clumped together over thousands of years, eventually growing into the moon-sized body we now call Titan. A competing hypothesis suggests something more dramatic, that Titan may have formed later and more violently, through a series of massive collisions between smaller icy moons that once orbited Saturn, their shattered remnants eventually reassembling into the single large moon we observe today. Each scenario would leave a different chemical signature behind subtle variations in isotope ratios, in the exact proportion of heavier versus lighter atomic forms of nitrogen and carbon, locked into Titan's atmosphere and ice like a kind of geological fingerprint. And when scientists carefully compared Titan's nitrogen signature to nitrogen found in comets' icy leftovers from the solar system's earliest era, preserved largely unchanged in the distant, frozen reaches beyond Neptune, the match was strikingly close. This single comparison strengthened the case that Titan's earliest building blocks came from far beyond Saturn's current orbit, material that formed in the bitterly cold outer edges of the solar system before gradually migrating inward over millions of years, eventually accumulating into the moon you are now imagining standing on. But here's where the mystery deepens even further. Because if Titan's raw materials genuinely originated that far out in the solar system, in a region so cold that even nitrogen exists as solid ice rather than gas, then Titan may be chemically closer to a comet than to almost any other moon orbiting any other planet in our solar system. Closer, in some fundamental sense, to the ancient, unprocessed material that built the solar system itself, than to the more typical rocky and icy moons we find elsewhere among Saturn's many smaller satellites. This would help explain something that has puzzled scientists for years: why Titan looks so fundamentally different from its smaller, icier siblings, orbiting the same planet moons like Mimas, Tethys, or Dione, each largely inactive, geologically frozen in place, with no atmosphere and no liquid cycle of any kind. Titan alone, among all of Saturn's many moons, somehow received or somehow retained the specific mixture of ingredients needed to build an active, atmosphere-bearing, chemically dynamic world. Was it simply a matter of size, with Titan growing just large enough to hold on to its atmosphere where smaller moons could not? Or did Titan form under genuinely different conditions, accumulating different raw materials than its neighbors, shaped by a different chapter of Saturn's early history? Scientists still don't have a complete answer, and that uncertainty itself is part of what makes Titan's atmospheric mystery so quietly compelling, because solving it wouldn't just explain one strange moon. It could reveal previously hidden details about how an entire system of moons, planets, and rings first came together over 4.5 billion years ago in the cold, swirling material that once surrounded a much younger Saturn. But even this remarkable nitrogen story only explains part of Titan's hazy orange sky, because nitrogen alone does not explain everything happening inside it. High above the surface, sunlight, faint as it is, at Saturn's great distance still interacts with that nitrogen and a smaller but crucial second ingredient, methane. And when sunlight breaks methane molecules apart in Titan's upper atmosphere, something happens that scientists did not fully anticipate when they first sent spacecraft to study this moon. The broken fragments of methane and nitrogen don't simply drift away, they recombine. They form long chains of complex carbon-based molecules, heavier hydrocarbons, that drift slowly downward through the atmosphere, like an endless, gentle orange snowfall, settling across the surface over millions of years. This process is the very reason Titan's sky glows, that deep amber orange color you saw the moment you first imagined standing there. It is also the reason scientists describe Titan's atmosphere as a kind of natural laboratory for organic chemistry, strikingly similar, in some basic ways, to processes researchers believe occurred on early Earth, long before life ever emerged here. But sunlight is not the only source of energy driving this process. There's a second, less obvious power source quietly at work, one tied directly to the massive planet Titan orbits. Saturn possesses an enormous magnetic field, generated deep within its interior, which traps charged particles, electrons, and ions, many originating from the solar wind, others escaping from volcanic activity on Saturn's moon Enceladus, into a vast, invisible magnetosphere stretching far beyond the planet itself. Titan's orbit frequently carries it directly through the outer edges of this magnetic shield, exposing its upper atmosphere to a steady bombardment of these high-energy charged particles. Scientists soon discovered that this particle bombardment is just as important as sunlight in driving Titan's complex atmospheric chemistry. In fact, in Titan's uppermost atmospheric layers, charged particles from Saturn's magnetosphere may contribute even more energy to breaking apart methane and nitrogen molecules than the sun's faint light manages to provide this far from its source. This means Titan's organic chemistry isn't simply a product of distant sunlight, the way Earth's biological processes overwhelmingly are. It's a partnership between two separate energy sources, one arriving from 90 million miles away, the other generated by the very planet Titan has orbited for over 4 billion years. Two different parents, in a sense, both quietly contributing to the same vast chemical legacy, now drifting down onto Titan's dunes, lakes, and frozen plains. Which raises an unavoidable question. If Titan's atmosphere is quietly manufacturing complex organic molecules right now, today, drifting down onto its surface in a slow chemical snow that has likely continued for billions of years. Powered by two separate cosmic energy sources working in tandem, what exactly is waiting down there, underneath all that orange haze? And what happens when that endless organic snowfall finally reaches the ground? What does the surface of Titan actually look like once you get past that thick orange sky? For decades, scientists assumed Titan's surface would be relatively simple, mostly ice. Perhaps some frozen lakes, a few craters scattered here and there, much like many of the solar system's other icy moons. What they found instead, when radar finally pierced through that thick haze, left planetary scientists quietly stunned. Stretching across Titan's equator are massive fields of towering dunes, some reaching as high as 100 meters, roughly the height of a 30-story building, extending in long, parallel rows for hundreds of kilometers across the landscape. From above, they look remarkably similar to the great sand seas of Earth's Sahara or Namib deserts. At first glance, it feels deeply familiar, Earth-like, even comforting. Discovering them at all required overcoming a significant engineering challenge. Titan's thick orange haze makes ordinary optical cameras nearly useless for mapping its surface in detail. The same haze that would block your view of Saturn's rings overhead also blocks most attempts to photograph the ground below from orbit. Cassini's solution was radar bouncing microwave signals through the haze and measuring how they reflected back, building up a detailed picture of surface texture and shape one narrow swath at a time, across dozens of careful flybys conducted over more than a decade. It was through this patient, repeated radar mapping that scientists first realized just how much of Titan's surface, by some estimates, as much as 17% of the entire moon is covered in these dune fields, making them one of the most widespread surface features anywhere on Titan, rivaled in extent only by the icy plains and the polar seas themselves. But that wasn't the strangest part, because the sand forming Titan's dunes is not sand at all, not in the way you understand sand on Earth. It is not crushed rock. It is not silica. It is something almost impossible to imagine standing on a beach made of tiny, solid grains of frozen hydrocarbons and organic compounds, formed from that endless atmospheric snowfall slowly settling onto the surface over countless millions of years. In other words, Titan's sand used to be sky. Each individual grain may represent a tiny fragment of complex atmospheric chemistry, manufactured high above the surface by sunlight breaking apart methane and nitrogen molecules, then drifting downward in a process that has likely continued, quietly and consistently, for a length of time longer than complex life has existed on Earth. If you reached down and let a handful of this material run between your gloved fingers, you would be holding billions of individually formed organic particles, each one a tiny chemical memory of Titan's atmosphere. And here is where the next mystery begins. Because for these dune fields to exist to be shaped into the long, wind-swept ridges scientists observed stretching across Titan's equator wind had to move them, consistently, predictably, over an enormous span of time. But Titan's winds, according to early atmospheric models, should be remarkably gentle. The thick atmosphere and Titan's slow rotation should produce only mild, steady breezes near the surface, nowhere near strong enough to lift and sculpt towering dunes the way scientists observed. So how were they formed? Researchers eventually proposed something elegant. that Titan's dunes were shaped not by daily wind patterns, but by rare, powerful seasonal wind events, intense bursts of atmospheric movement triggered roughly once every Titan year. As Saturn's slow orbit shifts sunlight distribution dramatically across the Moon's surface, and here lies something extraordinary to sit with for a moment. 1 year on Titan lasts 29.5 Earth years. This means each seasonal cycle, the gradual shift between Titan's version of spring, summer, autumn, and winter, unfolds across nearly 3 decades of Earth time. A single season on Titan could last as long as 7 Earth years. If you stood on Titan's equator and watched these dune fields slowly shift, century after century, you would be witnessing a landscape evolving on a timescale almost too vast for a single human lifetime to fully experience. But the dunes hold one more secret. Because their orientation, the precise direction they point, the pattern of their ridges did not match what scientists initially expected based on Titan's general wind models. The dunes seem to be shaped by winds, blowing in a direction the existing models simply didn't predict. This single discrepancy quietly forced scientists to reconsider how Titan's atmosphere actually circulates, suggesting unexpected complexity in how Saturn's gravity, Titan's slow rotation, and seasonal sunlight changes combine to create wind patterns far more intricate than anyone initially modeled. The answer researchers eventually settled on was almost poetic in its strangeness. The dunes are shaped primarily by rare, intense storm-driven winds that occur only briefly around Titan's equinox, the relatively short window, just a few Earth years long, when sunlight strikes Titan's equator most directly during its decades-long seasonal cycle. For the overwhelming majority of each Titan year, the dunes sit nearly motionless, sculpted slowly, in brief, violent bursts, separated by years of near-total calm. This means that if you stood among Titan's dunes for an ordinary stretch of time, even several Earth years, you would likely witness almost no visible change at all. The landscape would feel eternal, frozen in its current shape, the orange grains resting silently beneath a hazy sky. And then, once every few decades, for a brief season, the wind would finally rise. But that wasn't the strangest part. Because when scientists examined the chemical composition of the dune material more closely, using a combination of radar reflectivity data and infrared spectroscopy from Cassini, they discovered the grains weren't uniform. They appeared to be layered, composed of a core of one type of organic material, coated in a thin outer layer of a slightly different compound, almost like a tiny multi-layered pebble, repeated by the billions across the dune fields. Researchers believe this layering might explain how the grains formed in the first place, an initial particle, likely formed high in the atmosphere through the same methane and nitrogen photochemistry we explored earlier, slowly drifting downward while accumulating additional material along the way, layer by layer, like a snowflake very gradually built around a tiny central seed. If this theory holds, then each individual grain within Titan's dunes essentially tells a small story of its own formation, a record, in miniature, of conditions in Titan's atmosphere at the moment it formed, sealed inside a particle that may have then sat motionless on the surface for thousands or even millions of years before a rare seasonal storm finally moved it into the dune field where it now rests. This raises something worth pausing on. When Dragonfly eventually lands among these dunes and gathers samples for direct analysis, It won't simply be studying sand. It will be studying a kind of geological archive, countless individual records of Titan's atmospheric history, compressed into grains small enough to sift through gloved fingers, yet old enough that some of them may have formed before complex life had even fully established itself here on Earth. And this is where things become even more fascinating. Because dunes are not the only large-scale feature shaped by Titan's atmosphere. There is something else waiting near the poles, something liquid, something vast, and something that, when it was first discovered, completely redefined what scientists believed an alien moon was capable of holding. What would it feel like to stand on the shoreline of an alien sea? Before we reach that shoreline, there's something worth imagining first, something many people are surprised to learn you would almost certainly never see at all, despite standing on a moon orbiting one of the most photographed planets in our entire solar system. If you looked straight up, hoping to catch a glimpse of Saturn's magnificent rings hanging directly overhead, you likely wouldn't see them, not clearly at least. Titan's thick orange haze, the very same one we've described scattering and diffusing sunlight throughout this entire journey, would scatter that view as well, reducing one of the solar system's most spectacular sights into, at best, a faint, ghostly smudge of slightly brighter haze in one general direction of the sky. This is something many people find quietly disappointing when they first learn it. We tend to imagine standing on Titan with Saturn's rings stretched dramatically across the entire sky, the way artists have illustrated it for decades. The reality, according to atmospheric scientists who model Titan's haze in detail, would likely be far more subtle Saturn present, technically, somewhere up there, but hidden, much like trying to spot the full moon through a thick layer of Earth fog. Yet perhaps that, too, fits the quiet, mysterious character of this entire moon. Titan doesn't offer its secrets easily. Even the most spectacular sight in its home system, the rings of the planet it has orbited for over 4 billion years, remains modestly, almost humbly, hidden behind its own perpetual veil. Near Titan's North Pole, spread across an area larger than the 5 Great Lakes of North America combined, lies Kraken Mare, the largest known body of liquid anywhere in the solar system beyond Earth itself. It stretches for over 1,000 kilometers. It is deep enough, in certain regions, to fully submerge entire mountain ranges. And if you stood at its edge, watching gentle waves drift slowly across its dark, glassy surface, you would be witnessing something no human being has ever personally seen. Because Kraken Mare is not made of water. It is a sea of liquid methane and ethane chemicals that on Earth exist primarily as flammable gas. Here, in the extreme cold of Titan's surface, those same chemicals condense into a calm liquid form, settling into vast basins and forming an entire alien hydrological system. Yet what surprised scientists most wasn't simply that liquid existed on Titan's surface. It was just how familiar the entire system appeared to be. Rivers feed into these seas, carved gradually into the icy bedrock below, exactly the way Earth's rivers carve valleys over time. Smaller lakes dot the polar landscape nearby, some perfectly circular, suggesting they may have formed in a manner similar to how certain lakes form on Earth through a slow chemical erosion process, not entirely unlike how acidic water dissolves limestone back home. Scientists soon discovered that Titan even experiences something remarkably close to Earth's water cycle, except built entirely from methane instead of water. Methane evaporates gently from these seas under Titan's pale, diffused sunlight. It rises into the atmosphere, forms thick orange clouds, and eventually falls back down to the surface as rain, slow, heavy rain. Falling gently through Titan's thick atmosphere and weak gravity, taking far longer to reach the ground than raindrops ever take on Earth. If you stood beneath one of these rare methane rainstorms, scientists estimate the individual droplets would fall in a slow, almost hypnotic descent, large, heavy globules drifting down gently through the haze, moving at a fraction of the speed Earth's raindrops fall, due to Titan's combination of thick atmosphere and weak gravity. It would look less like a storm and more like a quiet, suspended shower of liquid hydrocarbon, beautiful, eerie, and almost meditative to witness. But that wasn't the strangest part of Titan's liquid cycle, because when the Cassini spacecraft examined Titan's seas more closely, scientists noticed something deeply unusual happening along certain shorelines, features that seemed to appear, then mysteriously vanish, in images taken just years apart. Researchers nicknamed this phenomenon the Magic Islands. Bright, mysterious features would suddenly appear on radar images of Titan's seas, only to disappear in later observations, then sometimes reappear again in a slightly different location. For years, the cause remained genuinely uncertain. Some scientists proposed that these features were waves, methane waves, rippling gently across the surface in patterns subtle enough to dramatically change how radar signals reflected off the liquid. Others suggested they may have been rising bubbles of nitrogen gas, slowly escaping from beneath the liquid surface and briefly disturbing it before settling again. A third possibility, even stranger, suggested these could be floating clusters of solid organic material, icy rafts of frozen hydrocarbon debris, drifting gently across the methane sea before eventually sinking back beneath the surface. To this day, scientists have not definitively confirmed which explanation is correct. There's another detail about these seas that deserves a quiet moment of its own. Despite their immense size, Titan's largest seas are surprisingly calm. When Cassini's radar measured surface roughness across Kraken Mare and its neighboring seas, the data suggested wave heights of only a few centimeters at most, even accounting for whatever winds might occasionally sweep across the surface. This is far calmer than almost any large body of liquid on Earth, where wind-driven waves regularly reach far greater heights, even on lakes a fraction of the size. Researchers believe the explanation lies in the unique combination of Titan's weak gravity and its dense atmosphere. Lower gravity means waves require less energy to form. Yet that same dense atmosphere creates enough resistance to dampen their growth before they can build into anything dramatic. The result is something almost meditative: vast seas, larger than entire countries, yet rippling so gently that standing at their shore might feel more like watching a sheet of dark glass than witnessing genuine open water. If you listened closely near that shoreline, scientists speculate you might hear something closer to a soft, slow lapping sound, rather than the crashing waves familiar from any ocean coastline on Earth, a detail that adds yet another layer to just how genuinely peaceful, despite its alien chemistry, a visit to Titan's seas might actually feel. But not every body of liquid on Titan behaves the same way. Smaller lakes scattered closer to the equator, in particular one studied closely by Cassini, named Ontario Lacus, revealed yet another unexpected wrinkle. Its shoreline appeared to be retreating over the years Cassini observed it, suggesting the lake was slowly evaporating, shrinking visibly across the duration of the mission. A process scientists linked directly to where Titan happened to be within its decades-long seasonal cycle. This single observation confirmed something profound, that Titan's surface liquid bodies are not simply static geological features. They are dynamic, breathing parts of an active climate system, expanding and contracting across Titan's long seasons, exactly the way certain lakes on Earth shrink during drought and refill during wetter years, except stretched across a timescale of decades rather than seasons. And this is where things become even more fascinating. Because if Titan's smaller lakes shrink and expand with the seasons, what happens to all that displaced liquid? Where does it actually go during the portion of Titan's year when evaporation outpaces rainfall? The leading theory suggests it migrates underground, seeping into a porous layer beneath the surface, sometimes called an alkanophore, a methane-based equivalent to the underground water aquifers found here on Earth. If true, this would mean Titan hosts not just visible surface seas, but a hidden, shallow subsurface plumbing system of liquid hydrocarbons, quietly redistributing material between the surface and a shallow underground reservoir across each long seasonal cycle. This subsurface liquid layer is entirely separate from the much deeper, much larger hidden ocean of water we're about to explore, meaning Titan may actually have three distinct liquid systems operating simultaneously: the visible surface seas, a shallow underground reservoir of liquid hydrocarbons, and a deep global ocean of liquid water far below. Three separate liquid worlds, nested within a single moon, each operating according to its own rules, its own chemistry, and its own timescale. The seas themselves, it turns out, may hold an even deeper secret, something related not to what floats on top of them, but to what might be happening far below them, deep beneath Titan's icy crust. If Titan's surface is so cold, so alien, so utterly unlike the conditions that support life as we understand it, why do so many scientists still consider it one of the most promising places in our solar system to search for life? The answer is not found on the surface at all. It's found far beneath it. When Cassini studied Titan's gravity and how the moon subtly wobbled during its orbit around Saturn, scientists noticed something that didn't match a solid frozen world all the way through. Titan's rotation showed slight irregularities, small variations that suggested its outer icy shell was not rigidly connected to whatever lay beneath it. This single observation pointed toward an extraordinary possibility that hidden beneath Titan's icy crust, possibly 50 to 100 kilometers down, lies a vast global ocean of liquid water. Not methane, not ethane, actual liquid water, sealed away from the freezing surface above by a thick shell of ice, kept liquid by heat generated deep within Titan's core heat, created largely through a process called tidal flexing, where Saturn's immense gravity continuously stretches and compresses Titan slightly as it orbits, generating internal friction and therefore warmth deep within the moon. If this hidden ocean truly exists, and the evidence strongly suggests that it does, it would mean Titan holds two separate liquid worlds within a single body, one on the surface made of methane and ethane, shaping rivers, lakes, and rainfall, and another deep below, made of liquid water, sealed away from sunlight, hidden from the orange haze above, existing in complete and permanent darkness. But the gravity data wasn't the only clue. Scientists soon discovered a second, independent line of evidence, hidden in something almost no one would expect to reveal information about an internal ocean, Titan's rotation speed itself. When researchers tracked Titan's surface features across more than a decade of Cassini observations, they noticed something that shouldn't happen if Titan were a single, solid, rigid body all the way through. The moon's rotation appeared to wobble slightly, speeding up and slowing down in small, measurable increments, in a pattern inconsistent with a rigid interior. The most natural explanation was that Titan's outer ice shell is mechanically decoupled from its rocky interior core floating, in effect, on top of a layer of liquid water sandwiched between them. That liquid layer would allow the icy shell to shift independently, slightly out of sync with the core's rotation, exactly the kind of subtle wobble Cassini detected. It's a remarkable piece of detective work, confirming an ocean hidden beneath dozens of kilometers of solid ice, on a moon nearly 1.5 billion kilometers away, using nothing more than how its surface features speed up and slow down by fractions of a degree over the course of years. A thick shell of ice, kept liquid by heat generated deep within Titan's core heat, created largely through a process called tidal flexing, where Saturn's immense gravity continuously stretches and compresses Titan slightly as it orbits, generating internal friction and therefore warmth deep within the moon. But that wasn't the strangest part, because scientists studying Titan's internal ocean believe it may not be simple water at all. Evidence suggests this hidden ocean could be extremely salty, likely containing dissolved minerals, and potentially ammonia, which would help keep the water in liquid form even at extremely low temperatures, since ammonia naturally lowers the freezing point of water significantly. If true, this means somewhere beneath your feet, while standing on Titan's frozen surface, there could be a dark, briny, mineral-rich ocean larger in volume than every ocean on Earth combined, sealed beneath dozens of kilometers of solid ice, completely isolated from sunlight, yet kept warm enough to remain liquid by the same gravitational forces that on the surface shape Titan's slow seasonal cycles. Yet another mystery emerged when scientists tried to estimate exactly how thick that protective icy shell actually is. Some models, based primarily on Titan's gravity field, suggest the ice could be as thin as 50 kilometers in certain regions. Other models, incorporating additional data about Titan's internal heat flow, suggest a much thicker shell, closer to 100 kilometers or more. This matters enormously, because the thickness of that ice shell determines almost everything about whether and how surface material could ever realistically reach the ocean below. A 50-kilometer shell, while still extraordinarily thick by any human standard, would represent a meaningfully shorter journey for organic material slowly migrating downward through cracks, impact sites, or other geological pathways, compared to a shell twice that thickness. And this single unresolved number, the precise thickness of Titan's icy shell, sits at the very heart of one of the biggest open questions surrounding the moon's potential habitability. Not whether the ingredients for life exist on Titan, which increasingly appears likely in some form, but whether those ingredients have ever had a realistic pathway to actually meet each other. And here is where the central mystery of Titan truly begins to take shape. Because liquid water, combined with available chemical energy, and protected from harsh surface radiation by a thick layer of ice, represents nearly every basic ingredient scientists associate with environments capable of supporting microbial life, similar, in some ways, to the deep-sea hydrothermal environments here on Earth, where life thrives in complete darkness, far from sunlight, sustained instead by chemical energy rising from the planet's interior. Researchers are quick to stress that the presence of these ingredients does not confirm life exists on Titan, but it does mean that, structurally, Titan's hidden ocean checks nearly every box scientists look for when searching for potentially habitable environments elsewhere in the solar system. And this raises an inevitable question that quietly haunts planetary scientists. If Titan's surface chemistry, all of that organic material drifting down from the orange sky, settling into dunes, dissolving into rivers and lakes, somehow found a way to interact with that hidden, warmer, mineral-rich ocean far below, what kind of chemistry might be unfolding down there, completely unseen, protected from solar radiation, shielded by kilometers of solid ice, slowly working through complex organic material for potentially billions of years? No spacecraft has ever drilled through Titan's ice to find out. No mission currently planned has the technology to directly sample that hidden ocean. Some scientists have already begun sketching out what such a mission might eventually look like, concepts involving a heated probe slowly melting its way down through the icy shell. Similar in principle to proposed missions designed to explore Europa's ocean, or alternatively, missions that simply wait for natural cryovolcanic activity to bring ocean material up to the surface on its own, the way certain icy plumes already appear to do on Enceladus. For now, these remain early concepts, decades away from realistic funding or launch, requiring engineering breakthroughs in autonomous deep ice drilling that don't yet fully exist. But the mere fact that serious scientists are already designing hypothetical missions to directly sample an ocean we've never seen, based entirely on indirect gravitational evidence, says something remarkable about how seriously the scientific community now takes Titan's hidden depths. Which means, for now, this remains one of the most profound unanswered questions about Titan, not what's visible on its strange orange surface, but what might be quietly happening in the darkness, far beneath it, hidden from every camera and every instrument humanity has ever sent there. But the surface chemistry itself holds yet another mystery, one that brings us directly back to the question of organic material, and why scientists believe Titan's surface chemistry might be uniquely important to understanding the deep origins of life itself. Why do so many scientists describe Titan as a natural laboratory for studying the chemistry that may have led to life? The answer lies in a substance that doesn't exist naturally anywhere on Earth in significant quantities, yet covers vast regions of Titan's surface in layers scientists are only beginning to fully understand. Remember that slow, continuous chemical snowfall, the organic material formed high in Titan's atmosphere, created when faint sunlight breaks apart methane and nitrogen molecules, allowing their fragments to recombine into increasingly complex chains. Scientists call these compounds tholins, a term originally coined to describe complex organic molecules that don't occur naturally on Earth, because our planet's atmosphere and surface chemistry are far too different and far too altered by billions of years of biological activity for them to form and survive here. Titan, by contrast, has spent billions of years quietly manufacturing them, completely undisturbed. These tholins are believed to include precursors to amino acids, the fundamental building blocks of proteins, and by extension, one of the essential ingredients required for life as we understand it. This does not mean Titan currently has life, or that these molecules alone are capable of becoming alive. But it does mean that Titan's surface chemistry shares deep similarities with theories describing the early chemical environment of ancient Earth, the same general category of chemical processes many scientists believe occurred here, slowly, patiently, long before the first microbial life ever emerged in our oceans, roughly 3.5 billion years ago. In other words, Titan may represent something extraordinarily rare, a real, observable, physically accessible example of prebiotic chemistry, the chemical stage that, theoretically, comes before life, but has not yet become life itself. This idea has deep roots in the history of science. Back in 1953, a young researcher named Stanley Miller, working alongside chemist Harold Urey, attempted something that, at the time, sounded almost like science fiction, recreating the conditions of early Earth's atmosphere inside a sealed glass apparatus, then passing electrical sparks through the mixture to simulate ancient lightning. Within just days, that simple experiment produced amino acids, the basic building blocks of every protein and every living thing on Earth, formed from nothing but simple gases and electrical energy, with no biology involved at any stage. It was one of the most famous experiments in the history of science, and it suggested that the chemical steps leading toward life might not require any special, rare conditions at all. They might simply require time, energy, and the right basic ingredients. Titan's atmosphere happens to closely resemble the gas mixture Miller and Urey used in their original experiment, rich in nitrogen and methane, much like the early Earth atmosphere they were attempting to simulate. Except Titan offers something that single laboratory experiment never could: an entire moon-sized version of the same basic chemistry, operating continuously for over 4 billion consecutive years, with energy provided not by simulated lightning, but by faint sunlight and charged particles streaming from Saturn's powerful magnetic field. And here is where things become even more remarkable. Because in 2014, scientists studying Cassini data identified something unexpected in Titan's atmosphere, a complex molecule called vinyl cyanide, found drifting in significant quantities at high altitude. Researchers had previously theorized that, under sufficiently cold conditions, this particular molecule could theoretically arrange itself into flexible, sheet-like structures eerily similar in basic function to cell membranes, the protective outer layer that defines and contains every living cell on Earth. Some researchers have even given this hypothetical structure a name: azotosomes, a theoretical alternative to Earth's cell membranes, built not from water-based chemistry, but specifically designed to function in Titan's freezing liquid methane environment. To be clear, this remains a theoretical possibility, not a confirmed discovery. No one has observed an actual azotosome. No one has detected anything resembling biological activity on Titan. But the very fact that scientists can construct a plausible, chemically consistent theory describing how a cell-like structure could function in liquid methane, using molecules Cassini directly detected drifting through Titan's atmosphere, quietly raises one of the most profound questions in modern planetary science. What if life does not require liquid water at all? What if life, somewhere in the universe, could be based on entirely different chemistry, methane instead of water, nitrogen-based membranes instead of carbon-based ones, operating at temperatures so cold that biological processes here on Earth would simply freeze solid? Researchers studying this possibility have given it a specific term: weird life, or sometimes, less formally, life as we don't know it, a category of theoretical biology built entirely around chemistry, fundamentally different from every organism ever discovered on Earth. If genuine methane-based biological activity exists anywhere within Titan's seas, even something almost unimaginably simple, it would represent a form of life operating at temperatures roughly 200 degrees colder than the coldest place on Earth where any known organism has ever been found alive. This concept even has a name among astrobiologists: the search for a second Genesis evidence of life that arose completely independently from Earth's biology, using fundamentally different chemical foundations, which would prove that life is not a rare cosmic accident, but a natural outcome that can emerge from multiple different chemical pathways under multiple different conditions throughout the universe. If Titan harbors even simple, methane-based biological activity, even something far more basic than the simplest microorganism on Earth, it would represent one of the single most important discoveries in the history of science. It would mean life is not fragile or rare. It would mean life is patient, adaptable, and willing to use whatever chemistry a given world happens to offer. There's a particularly important distinction researchers make when discussing this possibility, one worth sitting with for a moment. Methane-based biology, if it exists at all, would almost certainly operate at an extraordinarily slow pace compared to life on Earth. Chemical reactions simply happen more slowly in extreme cold, meaning any hypothetical Titan organism's metabolism, the rate at which it processes energy, grows, or reproduces, could conceivably stretch across years, or even centuries, for processes that take seconds or minutes in Earth's relatively warm biology. If true, this would mean that even if Titan's seas did host something resembling life, it might be almost undetectable to instruments designed around Earth's much faster biological rhythms, a form of life so patient, so slow, that proving its existence might require monitoring the same patch of liquid for years, watching for changes occurring at a pace closer to geology than biology. This single possibility, that Titan's life, if it exists, might simply be too slow for us to easily recognize, represents one of the quieter, more humbling challenges facing astrobiologists today. But here is the question that quietly underlies everything we've discussed so far. If Titan's surface chemistry is this promising, if Titan's hidden ocean checks nearly every box for habitability, if Titan's organic snowfall has been quietly building complex molecules for billions of years, why haven't we sent a mission specifically designed to search for direct evidence? The answer, as it turns out, is already in motion. How exactly do you explore a world where conventional wheeled rovers, the kind that have successfully driven across Mars for decades, might not even be the best tool for the job? Titan presents a unique engineering puzzle. Its surface includes towering dune fields, river channels, icy plains, and regions separated by considerable distance, all hidden beneath a thick, hazy atmosphere that makes orbital imaging far less precise than on most other worlds. But Titan also offers something almost no other planetary body in the solar system provides: a thick atmosphere, combined with remarkably low gravity. This rare combination means that flying through Titan's skies would require dramatically less energy than flying through Earth's atmosphere. The same thick air that creates strange floating footsteps for a hypothetical human visitor also makes it an unusually efficient environment for an aircraft to generate lift. NASA's solution, currently scheduled to launch and eventually arrive at Titan, is a mission called Dragonfly, a nuclear-powered rotorcraft lander roughly the size of a small car, equipped with multiple rotors, designed specifically to fly across Titan's surface, landing at one location, gathering detailed scientific data, then lifting off again to travel dozens of kilometers to an entirely new location. This approach is fundamentally different from any previous planetary mission. Instead of slowly driving across a single region the way Mars rovers do, Dragonfly is designed to leapfrog across Titan's diverse landscape, studying icy plains, then flying onward to investigate dune fields, then continuing toward locations where complex organic chemistry is believed to be especially concentrated. Each individual flight is expected to last roughly half an hour, carrying the lander between half a kilometer and several dozen kilometers, depending on the specific science objectives of that leg of the journey. Over the course of its planned mission, Dragonfly is expected to cover a cumulative distance of more than 170 kilometers farther than every Mars rover combined has traveled across the entirety of their missions, achieved here in a fraction of the time, thanks largely to that same thick atmosphere and low gravity we explored at the very beginning of this journey. Powering all of this is a radioisotope thermoelectric generator, a small nuclear power source that converts heat from the natural decay of radioactive plutonium into a steady supply of electricity. This same basic technology has powered numerous deep space missions before, including the Voyager probes, which continue transmitting data from beyond the edge of our solar system even now, decades after their launch. For Dragonfly, it solves an essential engineering problem. Titan's atmosphere is so thick and hazy that solar panels, reliable on missions to Mars, simply would not generate sufficient power this far from the Sun. Scientists soon discovered something especially compelling when selecting Dragonfly's primary landing region, an area near Titan's equator called the Shangri-La Dune Fields, located close to a relatively young, exposed impact crater named Selk. This particular crater matters enormously, because impact events like the one that formed Selk would have generated significant heat, likely melting underground water ice and creating, even if only temporarily, liquid water mixed directly with Titan's abundant surface organic material. Researchers estimate that any liquid water generated by the impact that formed Selk crater may have remained in liquid form for anywhere between a few hundred to several thousand years before eventually refreezing a remarkably long window. In chemical terms, for organic material and liquid water to interact directly, potentially producing more complex molecules than either ingredient could create entirely on its own. In other words, Selk crater may represent a location where, for some span of time after the original impact, two of the most essential ingredients scientists associate with life, liquid water, and complex organic chemistry, existed together, mixed directly, in direct physical contact with one another. If any location on Titan's accessible surface ever briefly created conditions resembling the kind of chemistry many scientists believe contributed to life's origin on early Earth, Cell Crater is one of the most promising candidates currently identified. But that wasn't the most exciting part of the Dragonfly mission. Because beyond searching for prebiotic chemistry, Dragonfly is equipped with instruments capable of directly measuring Titan's atmospheric composition, studying weather patterns in real time, examining the physical structure of dune material up close, and even listening for evidence of seismic activity tremors that could reveal information about Titan's internal structure, and potentially provide further evidence about that hidden underground ocean. One particular instrument aboard Dragonfly, a mass spectrometer paired with a drill capable of sampling material just beneath the surface, will be able to analyze Titan's organic chemistry at a level of molecular detail far beyond anything Cassini's distant orbital instruments could ever achieve. Where Cassini could detect the presence of complex molecules from high above, Dragonfly will be able to identify their precise structure directly on the ground, grain by grain. This means that, for the first time in history, humanity will have an explorer capable of directly walking, or rather, flying across the kind of landscape we've spent this entire journey imagining. The dunes, the frozen organic plains, the strange dim orange sky. Dragonfly will be there, physically present, gathering real data from a world currently known to us only through distant orbital imaging and remote sensing. And this is where things become even more fascinating. Because Dragonfly's mission timeline means that, depending on launch and travel duration, humanity's first detailed ground-level exploration of Titan could realistically occur sometime in the 2030s, meaning many people alive today may witness, within their own lifetime, humanity's first true up-close encounter with this extraordinary moon. The journey itself will take years. Much like Cassini before it, Dragonfly's path to Saturn will not be a straight line, but a long, looping trajectory designed to conserve fuel, using the gravity of other planets to gradually build speed along the way. Huygens it finally arrives and separates from its delivery spacecraft, Dragonfly will descend through Titan's thick atmosphere much as Huygens once did, except this time. Instead of a brief 90-minute transmission before falling silent forever, this lander will touch down, stabilize itself, and begin a mission designed to last for years. Scientists involved in the mission have described that first moment of landing with a quiet kind of anticipation, not just because of the engineering challenge involved, but because of what it will represent symbolically, the first time since Huygens, over 3 decades earlier, that any human-made object will rest directly on Titan's surface. 2 landings, separated by more than 30 years, both touching the same alien ground, the same strange orange haze settling around them in the moments after arrival. But Dragonfly raises its own quiet question, one that brings together everything we've explored so far. If this mission successfully detects complex organic chemistry mixed with liquid water near Cell Crater, if it finds molecular complexity beyond what Cassini was ever capable of detecting from orbit, what happens next? What is the next step scientists would need to take in order to determine whether Titan's chemistry has crossed or is close to crossing the line between complex chemistry and something resembling life? To understand that question fully, we need to step back and consider Titan not just as an isolated alien world, but within the much larger story of our entire solar system, and why Titan occupies such a uniquely important place within it. Is Titan truly unique, Or is it simply one example of something far more common throughout our solar system than scientists once believed? To answer that question properly, it helps to first understand just how large Titan actually is, because its size is part of what makes everything we've explored so far even possible. Titan is the second largest moon in our entire solar system, smaller only than Jupiter's moon Ganymede, and larger than the planet Mercury itself. If Titan orbited the Sun directly, rather than orbiting Saturn, many astronomers believe it would likely be classified as a planet in its own right, rather than a moon at all. This size matters enormously, because it directly explains why Titan succeeded in holding on to its thick atmosphere where so many other moons failed. Mercury, despite being a true planet, and despite being slightly larger than Titan, has virtually no atmosphere at all, largely because it sits so close to the Sun that solar wind and extreme heat strip away atmospheric particles far faster than Mercury's gravity can hold them. Titan, by contrast, combines just enough mass to generate meaningful gravitational pull. With extreme cold temperatures that dramatically slow down atmospheric escape, creating the rare, delicate balance required to retain a thick, stable atmosphere for over 4 billion consecutive years. For most of the 20th century, our solar system was imagined in fairly simple terms: a handful of rocky inner planets, a few gas giants, and a scattering of cold, lifeless moons orbiting them. Liquid water and the potential for life was assumed to exist almost exclusively on Earth. That assumption has been completely transformed over the past 3 decades. Scientists soon discovered that Europa, one of Jupiter's large moons, likely contains a vast subsurface ocean of liquid water beneath its icy shell, potentially containing more liquid water than every ocean on Earth combined. Around Saturn, another moon called Enceladus was found to be actively venting plumes of water vapor and ice directly into space, evidence of a subsurface ocean so dynamic that NASA's Cassini spacecraft was able to fly directly through these plumes and chemically sample them. When Cassini's instruments analyzed the chemical composition of Enceladus's plumes directly, in 2015, they detected something remarkable: molecular hydrogen, escaping alongside the water vapor and ice particles. On Earth, molecular hydrogen is frequently produced through chemical reactions occurring at deep-sea hydrothermal vents, the same kind of vents surrounded by thriving microbial ecosystems. Completely independent of sunlight, here in our own oceans. Its presence at Enceladus suggested similar chemical reactions, capable of providing usable chemical energy, might be occurring on the seafloor of its hidden ocean as well. This single discovery, on a completely different moon orbiting the same planet as Titan, dramatically reshaped how seriously the scientific community takes the broader question of ocean worlds throughout our solar system. If Enceladus, a moon barely 500 kilometers across, a fraction of Titan's size, could host chemistry this promising, what did that imply about the much larger, much more chemically active world orbiting nearby? Titan, in this context, is not an isolated anomaly. It is one of several ocean worlds scattered throughout our outer solar system moons that, despite orbiting far from the Sun in regions far too cold for life as traditionally imagined, may harbor vast bodies of liquid water hidden beneath their frozen surfaces, kept warm not by sunlight, but by the gravitational forces of the massive planets they orbit. But here is what makes Titan distinctly different from Europa and Enceladus, and why scientists consider it uniquely valuable. Titan is the only ocean world in our solar system that also has a substantial atmosphere, a complete surface liquid cycle, and direct access to surface-level organic chemistry happening visibly, continuously, right in front of any spacecraft we send there. Europa's ocean lies beneath miles of solid ice, with virtually nothing comparable happening on its frozen surface. Enceladus, similarly, offers little surface activity beyond its dramatic polar plumes. Titan, by contrast, offers scientists something extraordinarily rare, a fully observable surface laboratory of complex organic chemistry, actively happening today, combined with strong evidence of a hidden water ocean below, meaning researchers can study both layers of Titan's potential habitability simultaneously, using surface observations to infer what might be happening deep underground. And this is where things become even more fascinating, because some researchers believe that, given enough geological time, material from Titan's organic-rich surface could occasionally migrate downward toward its internal ocean, perhaps through impact events like the one that created Selk Crater, or through other geological processes still not fully understood, slowly carrying surface chemistry into contact with the warmer, mineral-rich water hidden below. If this kind of exchange genuinely happens, even rarely, even occasionally, it would mean Titan's two separate worlds, the frozen orange surface above and the hidden dark ocean below, might not be as isolated from each other as initially assumed. It would mean Titan could potentially host two entirely different types of chemistry, actively interacting with each other: traditional water-based biochemistry deep below, and entirely alternative, methane-based chemistry on the surface above, separated by nothing more than dozens of kilometers of solid ice. No other world currently known to science offers this particular combination. But Titan's uniqueness raises one more critical question, a question that brings together the entire scope of what we've explored across this journey so far. If Titan truly represents a preserved sample of the kind of chemistry that may have existed on early Earth before life first emerged here, and if Titan additionally hosts a separate, hidden ocean potentially capable of supporting more traditional water-based biology, then which version of habitability matters more, the visible surface chemistry we can observe directly today, or the hidden ocean we can only infer indirectly through gravity measurements and subtle orbital wobbles? This question sits at the heart of ongoing scientific debate, and the answer may ultimately determine where humanity focuses its search for life beyond Earth for decades to come. But before we can fully appreciate why this debate matters so deeply, we need to return to Titan's surface one more time to examine something that connects directly back to where we began this journey. The strange, hypnotic experience of simply standing there, beneath that orange sky, watching the slow rhythm of an alien world's weather unfold above you. What would it actually feel like to watch an entire season change on Titan? Remember, a single year on this moon lasts nearly 30 Earth years, meaning the slow rhythm of Titan's seasons unfolds at a pace almost impossible for a human mind to fully grasp through direct daily experience. Where Earth completes an entire cycle of spring, summer, autumn, and winter within 12 months, Titan stretches that same basic cycle across multiple human generations. If you stood at Titan's North Pole at the height of its winter, you would witness something remarkable: prolonged darkness, lasting not weeks, but years, as that pole tilts away from the sun's already faint light for an extended portion of Titan's orbit around Saturn. During this extended winter, scientists observed something Cassini was uniquely positioned to detect: massive cloud systems gathering specifically over the winter pole, distinct from the cloud patterns observed elsewhere on the Moon. These polar clouds appear directly connected to the methane cycle concentrated areas where evaporated methane gathers, circulates, and eventually falls back down as rain, feeding directly into the vast seas like Kraken Mare that we explored earlier. But that wasn't the strangest part of Titan's seasonal behavior, because as Cassini continued observing Titan across multiple years, scientists noticed something unexpected happening at the opposite pole, the pole experiencing its long summer season. A massive, mysterious cloud feature began forming high above the South Pole, completely unconnected to the methane cycle responsible for the polar clouds at the opposite end of the Moon. This cloud was composed of an entirely different chemical, frozen hydrogen cyanide, condensing at extremely high altitudes in a way scientists hadn't fully predicted. This discovery revealed something important: that Titan's atmosphere doesn't simply mirror Earth's water cycle, using methane as a direct substitute. It operates according to its own unique set of rules, shaped by multiple different chemical cycles operating simultaneously, each behaving according to different temperature thresholds, different altitudes, and different seasonal patterns. Scientists soon discovered yet another layer of complexity when they tracked how Titan's global cloud patterns shifted across the years Cassini spent in orbit. In Titan's earlier observed years, clouds gathered overwhelmingly near the South Pole, then experiencing its long summer season. But as Titan continued its slow, decades-long orbit around Saturn, and the seasons gradually shifted, scientists watched cloud activity steadily relocate toward the north, tracking, almost like a slow-motion compass needle, the changing balance of sunlight between hemispheres. This observed migration confirmed something scientists had long suspected but never directly measured across such an extended time frame: that Titan's atmosphere actively redistributes heat and moisture between hemispheres in direct response to its extraordinarily long seasonal cycle, just as Earth's atmosphere redistributes heat between hemispheres, except unfolding here across multiple decades instead of months. And this is where things become even more fascinating, because as Titan's decades-long seasons slowly shift, scientists observed entire weather systems migrating from one hemisphere to the other, methane clouds, and storm systems gradually relocating toward the hemisphere experiencing its long summer season, while the opposite hemisphere settled into its extended winter quiet. If you could observe this process across an entire Titan year, something no single spacecraft mission has ever fully accomplished, given how long that observation period would require, you would witness an entire Moon's climate system slowly breathing in and out, expanding and contracting, hemisphere by hemisphere, over the better part of 3 decades. There's one particular event scientists are still waiting for, with a kind of quiet scientific anticipation: a true equinox storm. During Titan's previous equinox, the brief seasonal window, when sunlight strikes the equator most evenly, Cassini detected a sudden, dramatic methane storm system forming near the equator, far larger and more intense than typical equatorial weather. Some researchers believe these rare equinox storms may be directly responsible for shaping and reshaping Titan's massive equatorial dune fields, providing the missing piece connecting Titan's seasonal weather patterns directly to its slowly shifting desert landscape. The next equinox-driven storm season, by current calculations, won't arrive again until the 2030s, meaning Dragonfly. Depending on its exact arrival and mission timeline, may have a genuine opportunity to witness, directly and up close, the very storm event scientists believe shapes the dune fields it will be flying across. But here's the deeper mystery hiding within this slow seasonal rhythm. Cassini's mission, despite lasting an impressive 13 years at Saturn, still only captured slightly less than half of one complete Titan year. This means scientists have never directly observed a full seasonal cycle on Titan, from beginning to end using a single continuous mission. Many of the patterns we currently understand, the polar cloud formations, the dune-shaping seasonal winds, the long-term behavior of Titan's massive seas, remain based on incomplete observational windows, carefully pieced together using a combination of direct Cassini observations, ground-based telescope monitoring, and increasingly, detailed observations made possible by the James Webb Space Telescope. In fact, Webb's infrared instruments have allowed scientists to continue monitoring Titan's atmosphere even after Cassini's mission concluded in 2017. Observing seasonal cloud changes and atmospheric chemistry shifts from a distance of well over 1 billion kilometers, using nothing but the faint infrared light reflecting off this distant moon. And recent Webb observations have revealed something scientists are still working to fully interpret: subtle, unexpected changes in cloud altitude and methane concentration that don't perfectly align with existing seasonal models, small inconsistencies that suggest Titan's atmospheric behavior may be even more complex and even more dynamic than current scientific models fully capture. Which means, even today, even with decades of dedicated observation, even with one of history's most successful planetary missions and the most advanced space telescope ever built, both contributing data, Titan's full seasonal story remains incomplete. We are, in many ways, still watching the opening chapters of a story that unfolds far slower than any human research career, waiting patiently for that orange, hazy world to reveal the rest of its rhythm. There's a quiet kind of poetry in how Cassini's own mission eventually ended, fittingly tied to Titan one final time. In September 2017, after 13 years orbiting Saturn, Cassini's fuel was nearly exhausted. Rather than risk an uncontrolled crash that might one day contaminate Enceladus or Titan with Earth microbes world scientists wanted preserved, pristine for future missions, searching for genuine extraterrestrial life, engineers used one final close flyby of Titan to bend Cassini's trajectory directly into Saturn's atmosphere, where the spacecraft burned up completely, becoming, in a sense, part of the planet it had spent over a decade studying. That final maneuver meant Titan's gravity, the same gravity that had quietly bent and shaped Cassini's orbital path dozens of times throughout the mission, delivered humanity's most successful Saturn explorer to its own ending. A fitting final gift from the moon it had done so much to reveal to us. But there's one final piece of this puzzle, perhaps the most quietly profound of them all, that brings together everything: the gravity, the chemistry, the hidden ocean, the patient seasons. It involves understanding exactly how old Titan truly is, and what its slow, careful preservation of ancient chemistry might be quietly telling us about the deep history of our entire solar system. If Titan formed at the same time as the rest of our solar system, roughly 4.5 billion years ago, why does its surface chemistry behave as though it's still in an early formative stage, almost as if time itself moves differently there? The answer lies in understanding exactly how Titan has spent those 4.5 billion years, compared to almost every other major world we know. Earth, during that same span of time, transformed dramatically. Its early atmosphere, originally rich in methane, ammonia, and other reducing gases, not unlike Titan's current atmosphere, was eventually replaced by an oxygen-rich atmosphere, fundamentally reshaped by billions of years of biological activity, volcanic processes, and plate tectonics constantly recycling its surface. Titan, by contrast, has remained in a kind of extended chemical adolescence. Without plate tectonics in the same active sense Earth experiences, without liquid water readily available on its surface to drive the same kind of geological recycling, and without billions of years of biological activity transforming its atmospheric chemistry, Titan has essentially continued performing the same fundamental chemical processes, slowly, patiently, largely unchanged, for billions of consecutive years. This is precisely why so many scientists describe Titan using a particular phrase, a frozen time capsule. Not frozen in the sense that nothing happens there. We've spent this entire journey exploring just how dynamic Titan actually is, with its rivers, seas, seasonal storms, and shifting dune fields. Frozen, instead, in the sense that the fundamental type of chemistry occurring on Titan today closely resembles the type of chemistry that may have occurred on early Earth, before our planet's atmosphere and surface were dramatically transformed by the emergence and eventual dominance of life. Scientists soon discovered that this comparison runs even deeper than general similarity. Detailed laboratory experiments, designed specifically to recreate Titan's atmospheric chemistry here on Earth, have successfully produced complex organic molecules, including amino acid precursors, using nothing but the same basic ingredients found in Titan's atmosphere: nitrogen, methane, and exposure to energy sources similar to Titan's faint sunlight and the charged particles streaming from Saturn's powerful magnetosphere. These laboratory experiments quietly suggest something extraordinary, that the basic chemical pathway potentially leading toward life's origin might not require Earth's exact ancient conditions at all. It might represent a far more universal chemical process, one that could occur, given sufficient time and the right basic ingredients, on multiple different worlds, under multiple different conditions, throughout our galaxy. Researchers at NASA's Goddard Space Flight Center and several other institutions have spent years running variations of these experiments, adjusting temperature, pressure, and energy sources to more precisely match conditions believed to exist in different layers of Titan's atmosphere. Each variation tends to produce slightly different combinations of complex organic molecules, suggesting that Titan's atmosphere isn't manufacturing just one type of prebiotic chemistry, but an entire diverse library of organic compounds, varying by altitude, by latitude, and by season. Some of these laboratory-produced tholins, when examined under careful chemical analysis, have revealed structures strikingly similar to compounds found in ancient meteorites here on Earth meteorites, believed to have formed in the same early, cold outer regions of the solar system that may have also contributed material to Titan's original formation. This connection suggests Titan's atmospheric chemistry isn't an isolated curiosity unique to one strange moon, but potentially a representative sample of a broader category of organic chemistry that occurred widely throughout the early solar system, most of which has since been destroyed, altered, or buried everywhere else except here. If that's true, Titan isn't simply a curious alien moon worth visiting out of scientific fascination. It becomes a working, physically accessible model for understanding one of the most profound unanswered questions in all of science: how did the universe's first living systems actually begin? Anywhere they may have begun, including right here on Earth nearly 4 billion years ago. And this is where things become even more remarkable. Because Titan offers something Earth's own ancient history simply cannot: directly observable, currently ongoing chemistry, happening visibly today, rather than chemistry scientists must try to reconstruct using only indirect geological evidence buried within nearly 4 billion years of Earth's own constantly recycled surface. Every time a spacecraft studies Titan's atmosphere, every time Dragonfly eventually lands near Selk Crater and analyzes its organic material directly, scientists aren't simply studying a distant moon. They are, in a very real sense, studying a living laboratory recreation of conditions that may closely resemble Earth's own distant, nearly unknowable past a chemical echo of the earliest chapter of our own existence, preserved not in ancient rock, but in active, ongoing processes happening right now, in real time, beneath that quiet orange sky. But this remarkable preservation also leaves us with one final, deeply humbling question. If Titan has spent over 4 billion years patiently performing this same fundamental chemistry, slowly, consistently, without rushing toward any particular outcome, what might it eventually become, given enough additional time? Could a moon like Titan, billions of years from now, eventually cross the same threshold Earth crossed nearly 4 billion years ago, the still mysterious threshold separating complex chemistry from genuine, self-sustaining life? No one currently knows the answer. And perhaps, for now, that uncertainty is precisely what makes Titan one of the most quietly extraordinary places in our entire solar system, not because we've found the answer there, but because Titan may be patiently working toward it, one slow methane raindrop, one shifting dune, one quiet seasonal cycle at a time, completely unaware that an entire species, 90 million miles away, is watching closely, waiting, and wondering. Let's return one final time to that quiet image we began with. You, standing on Titan's frozen surface, boots resting gently on a crust of solid ice, dusted with fine organic particles that drifted down from the sky above across more time than human civilization has existed. The orange haze stretching endlessly overhead, hiding stars you will never see directly from where you stand. A dark, glassy sea resting calmly in the distance, its surface occasionally rippling with mysterious features scientists still cannot fully explain. Take a moment to sit with how strange and how strangely peaceful this image truly is. Because everything we've explored across this journey, the floating, dreamlike gravity, the impossibly patient seasons unfolding across 30 Earth years, the slow chemical snowfall building dunes taller than city buildings, the hidden ocean sealed away in darkness beneath kilometers of solid ice, the quiet possibility of chemistry slowly, patiently approaching something resembling life, all of it unfolds at a pace almost entirely disconnected from the rhythm of human experience. We live our entire lives within roughly 80 or 90 trips around our sun. Titan completes a single one of its own seasonal cycles in nearly a third of that span. Its chemistry has been quietly developing for over 4 billion years, a length of time so vast that the entire history of human civilization, every empire, every war, every act of art or science or love would fit into the very last fraction of a single second if Titan's full timeline were compressed into something resembling a single day. And yet, despite this almost incomprehensible difference in scale, Titan feels strangely familiar to us. Its rivers carve valleys the way ours do. Its rain falls from clouds the way ours does. Its dunes rise and shift beneath alien winds the way deserts shift here on Earth. Perhaps this is the quiet central lesson Titan offers us, more than any single scientific discovery. That the universe does not need to copy Earth exactly in order to echo something deeply Earth-like. That familiar patterns, liquid cycles, seasonal rhythms, slow geological evolution may be fundamental processes the universe simply tends to produce, again and again, using whatever raw materials happen to be available in any given corner of space. Water here, methane there, carbon-based life on one world, perhaps, somewhere far stranger, an entirely different chemistry, quietly exploring its own version of the same ancient question. Are we alone? Titan does not answer that question directly. Not yet. Perhaps not for decades or even longer, as Dragonfly slowly makes its way across those vast dune fields, gathering whatever quiet evidence Titan has been patiently preparing for billions of years. But Titan does offer something equally valuable. In the meantime, a profound sense of scale. A reminder of just how vast, how patient, and how endlessly creative the universe truly is, capable of building entire functioning worlds from chemistry we associate here on Earth, with nothing more than fuel and exhaust. Consider, for a moment, everything that had to align for you to even imagine standing there. A star, our sun, had to form billions of years ago within a vast cloud of dust and gas. A planet large enough to capture and hold its own collection of moons had to form alongside it, far enough from that star to remain cold, yet close enough to receive at least a faint trace of its light. One of those moons had to grow large enough, at exactly the right distance, under exactly the right temperature, to hold an atmosphere thick with nitrogen and rich with carbon-based molecules. And somewhere, much closer to that same star, on a small rocky world entirely unlike Titan, a separate chain of almost equally improbable events had to unfold, eventually producing a species capable of building telescopes, then spacecraft, then finally, after 350 years of careful observation, capable of understanding what that faint point of light Cassini-Huygens once noticed truly was. Every step in that chain could have gone differently. Every step still might, on countless other worlds we haven't yet discovered, be unfolding in some entirely different direction, toward some entirely different outcome. And perhaps that is precisely why Titan feels the way it does, not frightening, despite its alien chemistry and impossible cold, but quietly, deeply calming. Because Titan reminds us that the universe is not in a hurry. It does not rush toward outcomes. It simply continues, patiently, methodically, for as long as it takes, whether that means 4.5 billion years of slow atmospheric chemistry on a distant moon, or 4.5 billion years of evolution on a small blue world much closer to the sun. When you look up at Saturn's faint golden glow in your night sky, if you ever happen to find it, drifting quietly among the stars, remember that hidden within that gentle light is an entire moon, slightly larger than our own planet's natural satellite, wrapped in thick orange haze, covered in seas of liquid gas, hiding a vast ocean of salty water deep beneath its frozen crust, slowly, patiently working through the same basic chemistry that may have once led, somewhere long ago, right here on Earth, to the very first stirrings of life. And perhaps that is the most calming thought of all, that somewhere out there, in the cold, quiet darkness beyond Saturn's rings, an entire world is still unfolding, still becoming whatever it is destined to become, completely undisturbed by time, completely unaware of being watched, simply existing patiently, quietly, beautifully, exactly as it has for over 4 billion years. There is something almost reassuring in that thought, if you let yourself sit with it for a while. Your own life, with all of its noise and motion and deadlines and worry, occupies a span of time so brief that Titan's slowest, most patient seasonal cycle would barely notice it pass. And yet here you are, capable of imagining that distant orange world in vivid detail, capable of caring about a moon you will never personally touch, capable of feeling, even now, a small and quiet sense of wonder about chemistry unfolding 900 million miles away. That capacity for wonder may be one of the most remarkable things our particular corner of the universe has ever produced. Whatever Dragonfly eventually finds near Selk Crater, whether it's nothing more than fascinating, lifeless chemistry, or something that quietly redefines our understanding of what life requires, the simple act of asking the question, of building a spacecraft and sending it nearly 1.5 billion kilometers to find out, says something profound about who we are as a species and what we choose to spend our brief, fleeting time here caring about. You don't need to understand everything about Titan to feel something when you imagine standing there. The slow rain, the floating steps, the endless orange sky. It is enough, sometimes, to simply imagine it, to let your mind drift gently across that frozen, hazy landscape, far from the noise and motion of your own daily life, and rest there for a while, in the quiet company of one of the universe's most patient, most mysterious worlds. Let that stillness settle over you now. Let your breathing slow. Picture, one last time, that quiet shoreline, the dark, glassy sea, perfectly still. The orange haze overhead, hiding stars you cannot see, hiding even Saturn's great rings, content to keep its secrets close. The faint, deep hush of an atmosphere too thick for true silence, too gentle for anything resembling violence, simply existing, the way it has existed for longer than human memory can comprehend. And somewhere, 900 million miles away, beneath a sky the color of amber, methane rain is still falling, gently, endlessly, the way it always has, and the way it will, long after we are gone. Rest now. The universe is patient. It will still be there when you wake.